If you like these videos, please hit the subscribe button and the notification bell. And if you would like to further show your support, please consider contributing to the channel on Patreon. The link is below in the description. Thank you. Last time we introduced partial derivatives, which is how we extend one variable derivatives to multiple variables. But that was just the first step. We haven't actually gotten a hold yet on how we're going to apply differentiation to multiple variables. Rather, the partial derivative is just the stepping stone or the tool that we use to build differentiation of several variables, which is where we're going. But we need one more concept before we start defining multivariable differentiation, and that is continuity in higher dimensions. So I was going to go straight into continuity in higher dimensions, but as I was working on it, I decided that it would be helpful for us to take a step back and review the basics of limits and continuity in one variable. Limits are fundamental to calculus. They're the underpinnings of both derivatives and integration, but after they're introduced at the beginning of calculus, I think we kind of forget about them. So it'll be good to review them. And of course, hopefully, if you haven't studied limits before, we'll go over them right now. So for the next 3 or 4 videos, we're going to develop the theory of limits and continuity of one variable. Then we'll move on back to multivariables. And in fact, from one point of view, you might say that once you understand limits, you understand all of calculus because the rest of it is just the application of limits. The derivative is the limit as h approaches 0 of f of x plus h minus f of x over h. And the integral is just another limit where you make the pieces smaller and smaller. So a limit is, first an intuitive definition, we write that the limit as x approaches a of f of x equals L if we can make the values of f of x as close as we want to this number by moving x closer and closer to a. So basically, the values of f of x come closer and closer to L as x gets closer and closer to a, but x does not equal a. So we can also say that f of x approaches L as x approaches a. So notice that x does not ever equal a. When we're looking at the value of a limit, we never consider what happens when x equals a. In fact, f of x doesn't even have to be defined at a. F of a might not exist at all. The only thing that matters is how f of x behaves near a. And this is super important because derivatives, for instance, would not even be possible without this detail. Because when h equals 0, of course, then this whole thing is undefined. I don't think this is emphasized enough when we first learn about limits, and you sort of have to grasp it on your own. But I think it's easy to miss this point, that when we're looking at this, we're never looking at h actually equaling 0. I remember when I first learned this, objecting that, but you can't divide by 0. The point is you're never dividing by 0. There's always going to be some value, and it's allowed to divide by anything, no matter how small, as long as it's not that one point at 0. Okay, so for example, let's guess the limit as x approaches 1 of x minus 1 over x squared minus 1. So notice, again, just like with the derivative, this is 0 when x equals 1. So this value does not exist at x equals 1. But we can get as close as we want to 1 and see if it's approaching something. So the point right now is just to get a sense of how limits work and look at how the values change as you approach a certain value of x. So I made a table here in Excel for various values of the function x minus 1 over x squared minus 1, just to see what happens as we get closer to 1. So as you approach 1 from the left, you can see it seems to be approaching 0.5. If we come at it from the other side with x bigger than 1, as we get closer to 1, then we're getting closer and closer to 0.5. So 0.5 would be a good guess for the value of this function as x approaches 1. Now, if we make a new function, just like the last one, but we give the function a value at 1. So let's say that g of x equals x minus 1 over x squared minus 1 if x does not equal 1, or 2 if x equals 1. So f of x looks a little like this. Looks something like that, but there's a hole right there. And then g of x is similar. There's still a hole at 0.5, but we defined g to be 2 at 1. So the point is, even in this case, if we had the limit, if we took the limit of this one as x approaches 1, even though at 1 the value of this function is 2, the value of the limit as x approaches 1 is still going to be 1 because it's still getting closer and closer on either side. So limits are intimately tied to the definition of real numbers. It's almost like real numbers and calculus are two sides of the same coin. We could even say that limits are the definition of real numbers, and real numbers are defined with limits in mind. They go hand in hand. The least upper bound property and the greatest lower bound property are exactly defined with the definition of limits in mind, and vice versa. So the previous example, where g of x had a different value at 2, it's very closely related to our videos examining the properties of real numbers. Because when we started looking at real numbers, the first thing we did was we observed that rational numbers have gaps in them. There's no rational number that equals the square root of 2. We can get as close as we want to that value, but we can never land on the square root of 2 in the rationals. And so we had, if we had a number line with the square root of p here, but it was only the rationals, we could get as close as we want. We can always find another rational in there on either side, but we can never get to this value, right? And that's exactly what limits are. It's about getting as close as you want. So the basic question of what is p when p squared equals 2 in the rationals could be written as the limit of, as x approaches 2 of the square root of x, could be written using the limit notation. So in this case, the limit definitely exists, but it's not in the rationals, right? So again, there's like a hole here. There's like a gap in the rationals. That was the whole purpose of making the real numbers, was to fill in all of those gaps. So if you haven't watched the videos where we examined the real numbers and constructed the real numbers using Dedekind cuts, then you should do that. Because it's all about limits. Even though we never talked about limits at the time, this was all the same concept of getting closer and closer to something without looking at the value actually at that number. Okay, so another example, the limit as x approaches 0 of sine x over x. So again, this is not defined when x equals 0, right? So if we look at a table of the values of this function as x approaches 0 from the left and the right, we can see that it's getting closer and closer to 1 on both sides. In fact, this function is symmetric about 0. It appears to be getting closer to 1, and that is, in fact, correct. But we can't prove it with the table. That's not good enough. We're going to have to get more precise with our definition of limit before we're going to be able to prove this. So a couple more examples. What about the limit as x approaches 0 of sine of pi over x? So what about this one? Here again, this number does not exist when x equals 0. But what can we see? What if we take some values close to 0? What are we going to see? If we take this at 1, it's just sine of pi, that equals 0. Let's get a little closer to 0, f of 1/2. That is, so if the 1/2 is down here, that's just the sine of 2 pi, that equals 0. If we do a third, that's just sine of 3 pi, that equals 0. If we do 0.1, that's just 10 pi, right? Because that's 1 over 10, that equals 0. If we do a 100th, that's sine of 100 pi. So it looks like, as we're getting closer and closer to 0, the value of this function is 0, right? It's not true. So although it is true that f of 1 over n equals sine of n pi equals 0 for any value of n, it's also true that f of x equals 1 for infinitely many values of x that approach 0. It just depends on which values you look at. So in fact, sine of pi over x equals 1 whenever sine of x equals pi over 2 plus 2n pi, right? Because if we have a circle, whenever the value is, if it's 0, 1 pi, 2 pi, 3 pi, 100 pi, 101 pi, sine is always 0 there. But if it's pi over 2, then sine is 1. 3 pi over 2, 5 pi over 2, 7, and so on. So, or any even multiple of pi plus pi over 2, and sine is 1. So if we solve for x here, then we get pi equals x pi over 2. So if we move this over here, then we have x equals... Actually, before we do that, if we multiply both sides by 2, then we have that 2 pi equals x times, and then if we just multiply the pi through the 2 through in here, we have pi plus 4n pi. Sorry, I'm getting a little small. Okay. And now if we divide this over, we have that x equals 2 pi over 4n plus 1 pi, divided through by pi, and we have that x equals 2 over 4n plus 1. So what that tells us is that if n here is an integer, then this function equals 0. But if x equals 2 over 4n plus 1, where n is an integer, then this equals 1. What's going on is that as it's always between 0 and 1, because sine is always between 0 and 1. But it kind of comes in here like this, and as it gets closer and closer to 0, it starts going faster and faster. And it comes in from the top, and it keeps going back and forth. So no matter how close you get to x, you're always going to be able to find any value between 1 and negative 1. So the limit of this does not exist. Okay. One more example. Find the limit as x equals 0 of x cubed plus cosine of 5x over 10,000. So if we look at a table for this function, as we approach 0, it looks like the value of this function is approaching 0 quite quickly. But if we actually just go down a little closer to 0, it turns out it's not actually going to 0 at all. In fact, it's landing on 0.0001. And there's a reason for that. X cubed is getting closer and closer to 0, but cosine of x as x approaches 0 gets closer and closer to 1. So there's always this extra tiny little bit here. So this part gets down to 0, but we're left with this tiny fraction. So the point of these two examples, in this case, by looking at some values in the table, we got it wrong originally because we didn't look at the right numbers. We didn't get close enough. And with the other example, with the sine of pi over x, there actually isn't a limit because it oscillates wildly as you get closer and closer to 0. It only looked like the limit was approaching 0 because we were choosing the wrong numbers for our table. So looking at some sample numbers simply is not reliable to find the limit of a function. We cannot guarantee with these random samples that we are really seeing what's going on. In order to prove either of these statements, we're going to have to make the definition of limit precise. So we need a way of stating mathematically, precisely, that if we have just a, say, simple function like this, that for some interval above and below this number, the value of the limit, we can find some interval around this point such that every value of x inside that interval will keep f of x inside the boundaries of this interval. So basically, if this is a, we need to have an interval here where this distance is we'll call it delta, and that as long as the, whoops, I drew that too big. As long as the value of x is inside this interval, then the value of f of x will be in this interval. And we'll call this interval epsilon. So this would be L plus epsilon, this is L minus epsilon, and then this value is L, and then that's A, and that's A plus delta, A minus delta. So what we want is that no matter what epsilon you pick, no matter how small it is and how close to L it is, then we can find a delta that will guarantee that for every value of x inside that interval, the value of f of x is always inside this interval on either side of L. That is how we define limits precisely. So, okay, the precise definition. Let f be a function defined on some open interval that contains the number a, except possibly at a itself. Then we say that the limit of f of x as x approaches a is L, and we write this if for every number epsilon greater than 0, there is a corresponding number delta greater than 0, such that the absolute value of f of x minus L is less than epsilon whenever 0 is less than the absolute value of x minus A is less than delta. And another way of saying this last line is that if 0 is less than x minus A is less than delta, then f of x minus L is going to be less than epsilon. So remember to always think of subtraction as the difference between two numbers, or the distance between two numbers. So, because when you try to think about this as actual subtraction, it just gets confusing that you have this value and then you subtract that value and then that's less than epsilon. What this means is that the distance between these two is less than this whenever the distance between these two is less than this. And then what the absolute value does is, it might be that f of x is above L or f of x is below L. So this number could be less than 0 or it could be greater than 0. All the absolute value signs are doing is that we're looking at the amount of the distance, not the direction of the distance. We don't need to know if it's above f of x or below f of x. We just want to know that that distance is less than epsilon. And same here. We don't care which side of A x is on, as long as it's within that distance. It's less than a distance of d away from A. So this definition of limits, then, can be expressed just in words like this, that the limit of f of x as x approaches A is L, means that the distance between f of x and L can be made arbitrarily small by taking the distance from x to A sufficiently small, so that however small you want the distance between f of x and L to be, you can always find a distance from A such that every value of x inside that distance will keep f of x inside the epsilon distance from L. Okay. So the definition can be reformulated in terms of intervals rather than distances. So when we say that x minus A is less than delta, we're saying that the distance between x and A is less than delta. We can manipulate this a little bit and get it in terms and look at it in terms of intervals instead. So if we have this, then that means that minus delta is less than x minus A is less than delta. And then if you just take A on both sides, we have that A minus delta is less than x is less than A plus delta. Okay, so just an interval. We have A minus delta, A plus delta on either side of x. Notice also that the part about it being that this distance being greater than 0, that is the formulation of x does not equal A. There has to be some distance, because if x equaled A, this would be 0. But this is not allowed in the distance, in the definition. And then similarly for f of x minus L is less than epsilon, we can rewrite that as L minus epsilon is less than f of x is less than L plus epsilon. So the limit definition can be stated in terms of intervals instead of distances by saying that the limit of f of x as x approaches A equals L means that for every epsilon greater than 0, no matter how small epsilon is, we can find a delta greater than 0 such that if x lies in the open interval of A minus delta comma A plus delta, but x does not equal A, then f of x lies in the open interval L minus epsilon comma L plus epsilon. So again, what this means is that if we have a function here and we have what we think the limit is, and we pick some epsilon, so that this is epsilon and this is epsilon. So this would be L plus epsilon and this is L minus epsilon. That no matter what epsilon we decide, here's L, we can find a delta such that, or this is A, sorry. we can find a delta such that if x is inside this interval, then f of x is going to be inside this interval. And then it's important to see that if we choose epsilon to be smaller, so that we're kind of closing in on it, then we're going to have to pick a delta that's smaller too, okay? But if the limit exists, what we have to prove is that no matter how small you get with your epsilon, we can always find a delta such that every value of f of x is going to be inside that value still. It's important to recognize that the process here where you take a smaller and smaller epsilon, it has to work for every positive value of epsilon, no matter how small. So if it has to be that no matter how small it gets, you're always getting closer and closer to x. That's what was wrong with the sign of pi over x, for instance. It was always getting outside of it. And if you wanted an epsilon that was less than 1, then you couldn't find a delta that would keep that function, this function. You couldn't find a delta that would keep this function within a certain value, okay? So that limit doesn't exist. So drawing a graph like this will show that it's probably true here. It seems like it's going to be true because the line is smooth, and so if you get smaller this way, you get smaller that way. But that doesn't prove it. We have to find a way to provide a delta for every epsilon. So we have to find so what we have to do in order to prove that a limit exists is that it's basically like a game or like a rule. No matter what epsilon you give me, I have to come up with some rule where I can plug the epsilon in and it'll spit back out a delta, so that no matter what you give me, I can just automatically give you, here's a delta that will make this work, okay? That's how you prove the existence of a limit and the value of a limit. Okay, so let's see how that works. So example. So let's try to prove that the limit as x approaches 3 of 4x minus 5 equals 7. So the way to do this is we're going to look at it and we're going to guess. We're going to try to find a guess for what a good value of delta might be. Then we're going to have to go back and actually prove that that delta works. And in math, that's frequently the way that you proceed with math. You can't just sort of prove it out of the blue. You need to have some kind of a guess that you're trying to prove, trying to get toward. So that's what we're going to do here. So first, let's just look at this and see if we can figure out what might be a good delta. And then we'll see if we can prove that that delta, in fact, works. So to plug this into our definition, we have f of x is 4x minus 5. And and L is 7, is less than epsilon, whenever x minus 3 is less than delta. And that's always greater than 0. Okay, so the absolute value of equals, just we can combine those. And then we can take out a 4 from this. And you can take a number out of the absolute value. Okay, so this is the same as this. These two things are equivalent. So that looks good because that's what we have here. So what we want is that 4x minus 3 is less than epsilon whenever 0 is less than x minus 3 is less than delta. In other words, divide through, the absolute value of x minus 3 is less than epsilon over 4 whenever, same thing, 0 is less than x minus 3 is less than delta. So we have the same thing here. So basically, if we make delta equal epsilon over 4, then this should work, because as long as epsilon over 4 is less than x minus 3, then that means that this whole thing is less than epsilon. So if we make delta epsilon over 4, this should always be true. Okay, but now we have to prove it. So this was just our guess. So now we have to prove it. So given epsilon greater than 0, we choose delta equals epsilon over 4. So okay, this is where these proofs can get really confusing, because we're juggling a lot of different things here, and it's really easy to get confused about which thing is dependent and which thing is independent, which thing we get to choose arbitrarily, and then which thing we have to take a certain value of, because the x supposedly is the independent variable of the function f of x, right? but then we're also choosing whatever epsilon we want, but then we're choosing the delta, but then we're also choosing the x. So it takes some time to wrap your head around what we're doing here. So what we want to prove is that for any epsilon greater than 0, so you can pick any one, and specifically no matter how small, because if you choose it to be 1,000, it's easy, but if you choose it to be, a millionth, then that's where it gets interesting. So you can choose any epsilon no matter how small, and we're going to prove that no matter what epsilon you give me, I can give you a delta that will keep f of x within that distance from L. So then this isn't an independent variable here. What we're talking about is we're only looking at values of x that are less than this distance from 3, from the A. So even though x is independent, what this really means is that what we want to know is that for the x's that are inside this distance, then we know that f of x will be this distance away. Okay? And so what we're really proving is we're not really choosing delta. What we're really proving here is that our rule is going to work. So that here's the rule that I want to prove, that will prove to you that this limit is true. Whatever epsilon you give me, I'm going to give you a delta that equals 1/4 of that epsilon. And then we're going to prove that no matter what epsilon is, with that delta, you'll always have f of x less than epsilon away. Okay? So what we're showing is that every x inside the interval of 3 minus delta, 3 plus delta, will give us this limit. We don't care if the x is outside. We want x that is an element of this interval. And then that interval gets smaller and smaller. Okay, so again, we showed above that the absolute value of 4x minus 5 minus 7 equals 4 times the absolute value of x minus 3. We showed that up there. So if 0 is less than x minus 3 is less than delta, then 4 times x minus 3 is less than 4 delta. And delta, we chose to be epsilon over 4, which equals 4 times epsilon over 4. We cancel the 4's, equals epsilon. So that's it. If x is inside this interval, then 4 times x minus 3 is less than 4 times delta, which equals epsilon. So if x is inside this interval, then we show that f of x is inside this interval. That's what we needed to show. So this can also seem backward because we're trying to prove the delta, but we're starting by going back to the f of x minus L. But what we're showing is that we're only looking at the x's inside this interval, and that if x is inside this interval, that means that this expression is going to be less than 4 delta, and that is the equivalent, is the same as epsilon, and this is what we needed to prove. So even though we started with epsilon, chose delta, then we're proving backward that this delta works, because if x is inside this interval, then f of x will be inside the interval that you gave me. Okay, so by the definition of limit, the limit of 4x minus 5 as x approaches 3 equals 7. So I want to talk about one last thing in this video, which is one-sided limits. And we've actually already encountered these in the videos where we proved the fundamental theorem of calculus. There were several times where we were looking at an open interval, and then we had to prove that the limit existed on the boundary of that open interval. And we used one-sided limits to do that. So, for example, there's something called the Heaviside function. Is defined as, so this function is 0 if t is negative and 1 if t is not negative. This function basically represents in electronics, if you close a circuit at time 0, then the signal goes instantly from 0 to 1. So what that function looks like is it's 0 all the way up to, but not including 0, and then it's 1 from then on. It's a very exciting function, isn't it? Okay, so the question is though, as t approaches 0 from the left, the value of this function is clearly 0. But as t approaches 0 from the right, the limit is clearly 1. So the limit of this function as t approaches 0 doesn't exist because our definition says that the value of the function needs to get closer and closer to some fixed value for t inside a narrower and narrower interval around 0. But this function approaches different values on either side of 0. So we can write this way. The limit as t approaches 0 from the left of ht equals 0. The limit as t approaches 0 from the right equals 1. So this means that it's approaching from the negative, from the left, and this means it's approaching from the right. Okay, that's what the minus and the plus mean. Okay, so what's a one-sided limit? So intuitively, the definition of this is almost the same as the regular definition. We just have one additional restriction on it. So we say that the limit of x as x approaches a from the left of f of x equals L, and we call this the left-hand limit if we can make the values of f of x arbitrarily close to L by taking x to be sufficiently close to A and x is less than A, okay? So it's approaching from the left. And there's one thing that's a little bit, you have to keep a little bit careful here, is that this is a minus sign, but that means that you're approaching to the right, like you're moving in a positive direction, but you're coming at it from the negative side. Whereas this one means that you're moving in a negative direction, but you're coming at it from the positive side. So there's a little bit of, you just have to, it's a little glitch there. You have to be careful about what that means. It means that you're on the left-hand side, but you're moving to the right. And then the right-hand limit means exactly the same thing, except that x is greater than a. So given this, the following is true. The limit as x approaches a of f of x equals L if and only if it equals that coming at it from both sides. So it means the left-hand limit equals L and the right-hand limit equals L. They have to equal the same thing or this limit does not exist. So notice here, what this means is the left-hand limit of the Heaviside function as t approaches 0 from the left does exist. It equals 0. And coming at it from the right, it does exist. It equals 1. It's just that they don't equal each other, so the limit of the Heaviside function as t approaches 0 does not exist. Okay, let's write down the precise definition of a one-sided limit. So just like the general limit, we can also express a one-sided limit in terms of delta and epsilon. So the limit as x approaches a from the left of f of x equals L if for every number epsilon greater than 0, there is a corresponding number delta such that the distance between f of x and L is less than epsilon whenever alpha minus delta is less than x is less than a. So x is within this distance of delta from a, but it's to the left of a. So this is like basically half of the interval. And then the right-hand limit would be exactly the same, except that it would be a is less than x is less than alpha plus delta. Okay, so this is right hand, this is left hand. So notice the general limit has the interval that we're talking about is alpha minus delta comma alpha plus delta. So the only difference here is that the left-hand limit restricts the interval to alpha minus delta or a minus delta comma a. And then the right-hand limit is x in the interval a comma a plus delta. Okay, so let's turn the page and do one example just to see how these work. So let's use the precise definition of the right-hand limit to prove that the limit of the square root of x as x approaches 0 from the right equals 0. So again, first we guess, then we prove. So remember, we're not guessing that this is true. What we need to guess is a delta that will make the function always within the distance epsilon. So we're guessing the value of delta. Okay, so let epsilon be any number greater than 0. In this example, L equals 0 and A equals 0. So we have to find delta such that, just putting it into our definition, the square root of x minus 0 is less than epsilon whenever, but now we're using the right-hand limit definition, whenever 0 is less than x is less than 0 plus delta, right? So it's a is less than x is less than a plus delta. So x is less than a distance of delta away from 0 on the right-hand side. So that just to rewrite that. we can do this because the square root is always positive, so we don't need the absolute value. So squaring both sides, we get that x is less than epsilon squared when. So now we have x on both sides, so this suggests that delta equals epsilon squared. Now, 2, prove it. Given epsilon greater than 0, let delta equal epsilon squared. So if x is between 0 and delta, then the square root of x is less than the square root of delta, and delta equals epsilon squared, so that's the square root of epsilon squared, which equals epsilon. And that's it. Because we showed that if x is within the distance on the right-hand side, delta, then the square root of x will be less than epsilon. That's what we needed to prove. Okay, that wasn't too bad. So of course, this answer is obvious intuitively, but it shows a couple things. First of all, it shows the necessity of one-sided limits because the square root of negative numbers do not exist in the real numbers. So this limit makes no sense if we took the general limit. We have to take the limit only going at it from the right. And then the second thing is, even though it's obvious that the square root of 0 is 0, saying it's obvious isn't a proof. We still need to be able to do it. And using these epsilon delta definition can be laborious, but it's necessary in order to prove something rigorously. Okay, so anyway, good. That is the definition of a limit. A couple of examples. So the next time we'll learn the limit laws, which will allow us to find the limits of a lot of complicated functions without needing to use the epsilon delta definition at all. But we have to kind of build toward that. So that's next time. Thank you for watching.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe. And please join me on Patreon. The link to that is below in the description. Thank you.